Hi everyone, welcome to part 2 of section 4.3. Now, in the previous video, we looked at what was called the standard normal distribution. In this video, we want to look at the non-standard normal, and then we want to look at how to find probabilities and percentiles in this scenario. Let's start off by talking about what is a non-standard normal. So before we define this, let's just reflect. Back in part 1, we said a standard normal is a normal distribution which has a mean equal to 0 and a standard deviation equal to 1. Now, if you have a case where your parameters are not 0, 1, like they both have to be 0, 1. So even if one of them is different, then automatically it becomes a non-standard normal. So if you had, let's say, 5, 1, even though this variance or standard deviation is 1, um, the mean is not 0, so it is non-standard. So it's strictly 0, 1 for it to be standard. Now, why is this relevant? Now, if you say that the mean is 0 and the spread is 1, remember, according to the empirical rule, almost all of the values lie between -3 and +3. However, in reality, I'm sure you know not all values lie in that interval. For example, you could have height. No one has a -3 height or a -2 height. So that means the mean is probably going to be something like, let's say, 100 or 150, and then there'll be a different spread, not necessarily equal to 1. So that results in all these different possible bell-shaped curves like these, where this mean might be something completely different from 0, and then the spread could be wider, it could be narrower, and something different from 1. So now the challenge here is, now if you want to find probabilities, we don't have tables for non-standard normals. We only have tables for a standard normal. So there is a trick so that we can use those same tables that we worked with earlier. We can take all of these distributions and convert them into a standard normal. And after we've converted them, then we can find probabilities for any normal distribution. And the way in which we do this is by what is called standardizing. So you can almost think of it as we are taking a non-standard and then we standardize it to make it a standard normal. Okay, a bit of a mouthful. And then ultimately you're converting any non-standard normal to a normal 0, 1. And there are tables for a normal 0, 1. So let's have a closer look at this normalization to see what exactly is happening here. Let's have a closer look at what is going on in this formula here. This formula is actually a transformation. Consider this example. X has a normal distribution with mean -3 and variance 0.2 squared. Now we know this is non-standard because the mean is not 0 and the variance is not 1. So remember I said if you have a non-standard normal, you can standardize it and convert it into a standard normal. So let's start off with the numerator where we subtract the mean. In this case, that's -3. So ultimately, the result of this, hopefully you remember from calculus, is this is actually a translation. It moves the entire distribution so that the mean is 0. So ultimately, x minus -3 will have a normal distribution with mean 0 and then an unchanged variance. So let's now look at the denominator. If you divide by the standard deviation, in this case, that's 0.2, what does this do? Okay, so remember x minus -3 becomes x plus 3. And then if you divide by 0.2, what happens there? It spreads out your data just like this and ultimately gives you a random variable with a mean and a variance of 1. So this first transformation shifts the whole distribution, so the mean is 0, and then dividing by the standard deviation will make your standard deviation equal to 1. So ultimately, this curve here is a standard normal. Okay, so that means if you have a probability in terms of x, you can convert it so that you end up with something in terms of z, and you can use the tables. So in your textbook, this leads us to this. So they're pretty much saying if you have some probability here and then there's x here. So the probability of being less than or equal to x is this shaded region. Then if you use this transformation, this x becomes x minus mu over sigma, and the shaded region actually remains the same probability. So that means if you find this probability in your tables, it's equivalent to finding this probability. All you've done is you've translated and pretty much squashed the same area down, but this area is still 1 and that's still 1. But then the transformation just makes it so that you can use the tables. So let's do an example together. Consider the following. So you have x, which is non-standard normal, and you want to find out what's the probability that x is less than or equal to 2. So let's treat it the way you do it in calculus. Whatever you do on the left, you do on the right. So if we subtract the mean on both sides, it would be 2 minus that minus 3. So always watch out for those signs. And then on this side, we left it as minus mu. We'll keep the symbols on the left and we'll use the numbers on the right. And then in the next step, we're still using this transformation. We're going to divide both sides by the standard deviation of 0.2. So like I said, we'll leave the symbols here. And then on the right side, that's where we'll end up with the numbers. Now, we know that this thing is the right-hand side of this transformation. So in the next step, we're just going to write it as z, because this is standard normal. So that's why we can use the letter z now. And then obviously the 25 comes from 5 divided by 0.2. And then in this case, remember this is a standard normal CDF, so you can also use a special notation that we use for a standard normal, which gives you that capital letter phi with 25 inside. And if you actually go to your normal tables, and if I ask you to find this probability, you wouldn't find 25 in there. But just ask yourself for a moment, what is the answer to this question? Because you should be able to tell me without even looking at the tables. If you came to the conclusion that the answer would be 1, then you are correct. Now, you might be wondering how if you weren't able to get it. So remember, for a standard normal, most of the probability lies between -3 and +3. 25 is well far away from 3. So the answer here, so all the probability, the entire distribution is going to lie to, well, most, like, like 99.999% will lie to the left of 25 because most of it already lies below 3. So 25 is just bigger than that. So ultimately, you would say the answer here is approximately 1. Let's consider a second example. Now, suppose I asked you to find the probability that x is between 1 and 2. You'd follow the same procedure. Whatever you do on the left, you do on the right. If you want to try it on your own, you can pause the video now and try it on your own. Otherwise, I'm going to continue. So you subtract the mean throughout the entire inequality. So on the left, you subtract -3, on the far right, -3, and also in the middle, you subtract the mean, but we're going to leave it symbolic in this case. Then you divide everything by the standard deviation, and then this term in the middle, from the previous example, you should know that becomes z, and then these just follow from your calculator. Now from here, we know this result. If you want to find the probability that x is between a and b, then it's f of b minus f of a. So in this case, our a is 20 and our b is 25. So you have probability that z is less than or equal to 25 minus z less than or equal to 20, which gives you this result. And this is also one of those cases you can immediately see what the answer is. Did you get 0? That's correct. So remember the area at the left of 25 is approximately 1, and the left of 20 is also approximately 1. So the answer would be approximately 0. So you just use the curly equal sign and say 0. So I want to give you an example to try on your own now. So try this quickly and then just pause the video and we'll look at the answer just now. All right. I hope you attempted it on your own. It's always good to try things on your own so that you learn how to do everything. If you got the answer of 0.9544, well done. Let's see if you got the working perfectly correct, which I trust you probably did. And in case you didn't, we'll still go through it for you as well. So if you want another example, there's example 4.22 in the textbook to also look at as self-study. So let's take this step by step, and you can use the same procedure for any other kind of probability question that you get with random variables. So step 1, formulate or identify the variable. So in other words, let's say you choose X or Y, whatever. Just specify what is it in words. So in this case, this is the measured resistance of a randomly selected wire. Okay. Then step 2, formulate the probability distribution. So in other words, identify, is it normal? Is it Bernoulli? Is it Poisson? And then also give the relevant parameters. So in this case, remember you're going to give the mean in the first position and then the variance. Note well, put the variance. Don't put the standard deviation. Put the variance. So in this case, the mean is 0.13 and then the variance is 0.005 squared. So don't just put 0.005 because that is not the variance. So I'm emphasizing it because I see a lot of times students go and put the standard deviation instead of the variance, and that's not correct for this representation. Step 3, identify the required probability. So in this case, they ask you to find the probability that y is between 0.12 and 0.14. I think, especially while you're still starting off, you should draw the curve for yourself and then shade it in so you can clearly see what you're looking for. As soon as you're more comfortable, you're welcome to leave it out. Now, this is clearly non-standard. So if we want to find probabilities, remember to standardize. So memorize this formula. It will not be given. You need to know how to standardize a random variable. So remember what this does is it converts these values that are in terms of y into values that are in terms of z. So you can think of it as a different scale. And this side now, if you take your zero point 0.2 and you subtract the mean of 0.13 and divide by 0.005, you get -2. On the other side, you get 2. So now to complete the working, you follow the same procedure that we did earlier. So in this case, you could actually do it whichever way you like. So do FA minus FB, if this doesn't make sense to you, you should come to the same answer. What they're doing here, though, so it's just a different way of looking at it, is they're taking 1 to be the entire probability, right? And then remember, we said this thing is symmetric. So that means the probability below -2 is the same as the probability above +2. So what you can do is just go to your tables and only look for this probability less than -2 and then double it. So that's where we're getting 1 minus 2 of your phi minus 2. So this should bring you to the final answer. So you'd get that 0.0228 from the tables, and then you'd have 0.9544 as your final answer. If this is confusing you, like I said, go back to that FB minus FA formulation. That will work too. Now let's talk about how do you find percentiles of an arbitrary normal distribution. Okay, so remember I like to describe finding percentiles as doing this whole process backwards, what we were doing earlier, but we did backwards. All right. So let's just start off here. So we know from everything that we've covered just now, if we want x less than or equal to some value of x, then we know it's equivalent to z less than or equal to the standardized version of that x. So we know this is true. All right. So like I said, now if you're going backwards, so let's say I don't give you x, but I give you this probability, which I'm going to call p in this case. The question is, if I want you to find a percentile, I'm giving you p, give me x. All right. Remember, my p is this probability here. And remember, these two things are equivalent. So this shaded region is actually the same as this shaded region. And mathematically, you know it because of this. So if I know this probability equals p, then even the standardized one is also equal to p. Okay. And then in order to, what we're asking you to find here is instead of a probability, we give you the probability and then you need to know this value. And following the notation from chapter 2, you could have written it this way. So eta zp would be this value and then eta xp is this value. So the whole idea behind trying to find a percentile is if you have eta zp, then you convert it back to eta xp, and then that will be the required percentile for this distribution for x. Okay, so let's have a look at it in a bit of a summary. So suppose you take this standardization transformation that we have here and you rearrange it a little bit. So I want to make x the subject. So I'm going to multiply both sides by sigma. All right, so that gives you z sigma on the left and then just that. And if you add mu on both sides, then ultimately the result is x is equal to z sigma plus mu. So what this tells you is summarized actually in this graph here. If you have an x, value of x, and you want to use the normal tables, then you use this formula to get to z. But now if you have a value of z and you want to convert it back to a value in terms of x, then you just use that transformation, just now rearrange so that x is a subject. So you put z times sigma plus mu and you put it in there. And I showed you where this comes from. It just comes from rearranging that probability, that formula there. So you only need to memorize this one because that one follows directly from it. So what does that mean for us? All right. Remember, I at this stage can only find probabilities and percentiles for a standard normal. I can't find one for a non-standard normal. So the trick here is you're going to find the percentile here and then convert it. Okay. So in other words, remember that's the formula we just derived from this one here. You're going to take whatever value you get here from your tables, NZP, and then you will just use this formula to convert it to a value for x. So remember, x is that thing that's non-standard, like it could be weight, it could be your marks for the class. So that's why you need to take whatever you find in your Z scale and convert it to the one you're actually interested in. So let's look at an example. Um, if you like, I think you should go ahead, pause the video, and try this example for yourself. You might be able to get it. Okay, so if you did try it on your own, you should have gotten 2.1516. If you did get it, well done. Well done. That's really, really good. You've done so well. And then this is pretty much what the working would have looked like. So here it's telling you that the area to the left is 0.975, right? So remember how you find percentiles for a non-standard case. You look for your 0.975 and then you go backwards and you'd get 1.96. But this is in terms of the Z scale. So what you need to do is use this formula to convert it to a value of x, which gives you that. Now I want to just show it now more explicitly and just rigorously so you can actually see how you come to that answer. Now with full working. So, in other words, what this question is asking you for is C, such that the probability of Y being less than or equal to C is 0.975. All right. So, this is non-standard. This is not 0, 1. Okay. So, you need to standardize it. So, I've just rearranged it. I took 0.975, put it on the left, and then copy this. And I know that this probability is equivalent to that one, provided I've standardized everything. So C minus 1.25 divided by 0.46. So that means now, okay, I don't have a table for this, but I do have a table for this. And from that table, I can find what this value is. And um, this value now, it corresponds to where I have my question mark here. So I know the area to the left is 0.975, and then I need to find this value here. And as I described earlier, it's 9.75. And remember, it's like finding probabilities backwards. So instead of starting out with your Z, you start inside your table, and then you go outwards, and then you find your Z. So what this tells us is this value is 1.96. So remember your tables give you left side probabilities. So you know for a standard normal, in order to have 0.975 on the left, this value would need to be 1.96. Okay. But remember, we're not interested in this case here. We're interested in Y, not Z. So what you need to do is find C, because C is the one that is relevant for Y. So I just took this part and I formed an equation. I said C minus 1.25 divided by 0.46 equal to 1.96. And if you solve this, this gives you your 2.1516. If you look at this part of the formula, okay, this is exactly equivalent to this. So it's like that standardizing formula, but now going back to your non-standard case. So remember mu is 1.25, which is what I have here. And then your Z value from the table is 1.96 and sigma is 1.46. So this is now how you get to the answer for any percentile, even if you want to do it later for one of our other distributions. It's the same kind of idea behind it. Now let's have a look at example 4.24. This one's in the textbook, but I want us to just walk through it. So the amount of distilled water dispensed by a machine is normally distributed with a mean of 64 ounces and a standard deviation of 0.78. What container size C will ensure that overflow occurs only 0.5% of the time? All right, so step one, we need to define what is our random variable, and we're going to call it X. So let X denote the amount dispensed. Okay, so the question here now, oh, before we do the question, let's do our step two, is what is the distribution of X now? So we're told the mean is 64 and the standard deviation is 0.78. So therefore, in this shorthand notation, you put 64, and remember this is the variance, so it's 0.78 squared. So watch out for that. Make sure you check in the question. Were you given the variance or the standard deviation? So now the question is saying what container size will ensure that overflow only occurs 0.05% of the time. So what this means, okay, we said X denotes the amount dispensed. So you've got this machine that is pouring liquid into a container. And now they're saying, okay, let's focus on this overflow term, right? So they've given a probability of overflow, right? So overflow will happen when the machine dispenses more than the capacity of the container. So in other words, when the amount dispensed, that's X, is greater than the capacity of the container, which is C. So in other words, whenever you have X greater than C, that is when you have overflow. The question is saying what container size will ensure that overflow only occurs with a probability of 0.005. Okay, so here you can hopefully immediately see that it's a question where they want the percentile because they gave you the probability in terms of a percentage, and then they wanted you to find a C. Usually we would say find a probability, and then you know it's that typical Standardize, use the tables. Now here we've given you the probability and we say find something. So this is how you take this statement and turn it to a mathematical expression. All right. Another way of looking at this that you can also go with is the probability that x less than or equal to c is 0.995. So let's just quickly break this one down, and then we'll continue from there. So here, um, remember x greater than c is when you have overflow. Remember x is amount dispensed greater than size of container. Now, here, you could have actually sketched this. Draw yourself a normal curve and just shade in the area at the right. You'll have 0.005. So that means the area at the left should be 0.995. And what does this mean now if you just look at it? So remember, x is the amount dispensed. So when you look at probability statements, this is like looking at a sentence. So x is the amount dispensed. So it's saying what's the probability that the amount dispensed is less than or equal to the container size? You see? So it's literally just taking this English verb, sentence and turning it into a math notation. So in other words, what's the probability that you do not have overflow? So it's like the complement of this case here. So this is overflow. This is not overflow. You will not have overflow when the amount you dispense is smaller than the size of the container. Now, the reason why we wanted to convert it like this is because our table only gives us left-hand probabilities. So this is something that you need to watch out for. Here, they know x is greater than c. Is that? But then the tables will only give you x less than or equal to a value. So that's why you needed to convert it into this form. It's the same c, okay? But we're just now focusing on the left-hand probability instead of the right-hand probability. Now let's go to our table. Table A.3 gives you left-hand probability, so it looks exactly like that. And we know that the value that we're looking for has 0.995 to the left of it. So we need to look here within the table for the probability of 0.995. Now, 0.995 isn't exactly there. So we're going to take the closest. If it lies perfectly in the middle, then we'll take the middle value. So in this case, 0.995 lies between 9949 and 9951. So it's right in the middle here. So it's about 2.57, and then we add the 5 because it's in the middle. If it was closer to this value, we'd take 0.57. If it was closer to that one, it'd be 0.58, but it's perfectly in the middle, so we're going to use 2.575. All right. But remember, this is in terms of your Z distribution. That's your standard normal. So that's not what they asked for. X is not standard normal. So we need to take that value of Z and then convert it to a value of X. All right, so we just rearrange this formula, and I've already found my eta ZP. Well, P would be 0.995, and then I'm going to use this formula to get my eta XP. Remember, my P is 0.995. So in this case, I like to use C because it's just easier to write, but it's equally correct to write eta 0.995. And then our mu is 64 from the question. And then we got this value from the tables here, 2.575. And then sigma is given in the question, 0.78. And if you solve this, you get 66 ounces. Now that brings us to the end of this section. I hope it was clear to you. Please do lots and lots of practice questions and don't be afraid to consult if you need assistance. Otherwise, this is the end. I'll see you in part 3.